This lecture is on the Schumpeterian growth model, and here I present the one-sector version. In the next video I will present the multi-sector version. This lecture is based on the article by Aghion and Howitt, published in 1992, A Model of Growth Through Creative Destruction, published in Econometrica, and I present a very simplified version of the model that is presented, for example, in the textbook by Aghion and Howitt, The Economics of Growth, published in 2009 by MIT Press. The starting point is that you know already that endogenous growth theory was basically invented by Paul Romer in his 1990 paper Endogenous Technological Change, but their technological progress is based on horizontal innovation. What does this mean? It means that every new technology is a new intermediate good. So you have a range of different goods that are produced in the economy, and technological progress is an expansion of the range of these technologies. However, it also implies that at a certain point in time, all technologies that have been invented before, so all old technologies and the new technologies, are used at the same time in production. So for example, the ox cart is used as well as the Tesla, and very modern technologies are used with very old ones. Aghion and Howitt were the first in 1992 to introduce a vertical innovation, which means that an innovation is an improvement of an old technology, and basically new technologies replace old technologies. And that gave this whole literature the name of Schumpeterian growth, because there is creative destruction. Every time a new technology is invented, the incumbent for the old technology is driven out of the market. So you have a creative destruction effect because the new technology replaces the old technology. Now let's jump directly into the model. Time is modeled as discrete, so that there is t, which equals to 1, 2, and so on and so forth, which denotes time. The economy is populated by L individuals. Again, we assume that the number of people in the economy is equal to the number of workers, so there are L workers. Each of them inelastically supplies 1 unit of labor on the labor market. The individuals are risk neutral and maximize the expected consumption level, and this is the sole determinant of utility. So there is no other component of the utility function, such as leisure and so on and so forth. The people consume a final good denoted by YT in the economy, and this good is produced with labor as one production factor, and an intermediate good denoted by X at time t, with an output elasticity of alpha, and labor has an output elasticity of 1 minus alpha. So it's a Cobb-Douglas production function. And AT now refers to the productivity of the intermediate. We will see later that this then translates into labor augmenting technological progress, basically, if AT evolves. The intermediate is produced by a monopolist. I will talk about this on the next slide. And the input in production is the final good in a one-for-one technology. So as a consequence of this, we have that GDP of a country is equal to output, but minus the value added in the intermediate goods sector, which is XT, because there is only one intermediate goods sector, so we have a one-sector economy, as I said at the beginning here. In the next lecture, we will talk about the situation when there is a range of intermediate goods, so a continuum of intermediate goods that are produced by different firms. Now, the intermediate goods producer makes profits, and these profits are denoted by pi t, and this is equal to the price that the intermediate goods producer can charge for its intermediate multiplied by the amount of the intermediate it produces, so that would be revenue, minus the cost of production. And the cost of production is equal to 1, that's the price of an intermediate in terms of the final good. And xt is the number of intermediates, or the amount of intermediates that this intermediate goods producer produces. So the costs of production are the price, which is 1 times production, xt. So total profit is revenue minus cost. Now the price function that the monopolist faces on the market is the inverse demand function from the final goods sector. So the monopolist or the final goods producer would basically be willing to pay the price PT as the marginal product of the intermediate to buy it in order to be able to produce. And we can compute this from the final goods production function when we take the derivative of yt with respect to xt. So we see alpha comes down from the exponent, atl to the power of 1 minus alpha stays unchanged, and xt, the exponent, is reduced by -1. Now this price, this function of the price as a function of the intermediate is the inverse demand function, and it's the side constraint in the profit maximization problem of the monopolist. So we can plug in this price here into this function and get the profit function afterwards, where we see that the price is multiplied by xt. So this xt here, the -1 drops out because we multiplied by xt. So we have xt to the power of alpha minus xt here. And that's the profit function that the intermediate goods producer, the monopolist, maximizes. And the first order condition for maximization with respect to xt is just the derivative of this function with respect to xt. So we see again alpha comes down from the exponent, it multiplies with this alpha here, so we have alpha squared. Again, this term here remains unchanged, atl to the power of 1 minus alpha. Here the exponent gets reduced by -1, and here the derivative of xt with respect to xt is 1, so we have -1 here, and this has to be equal to 0 for a profit maximum, and we can then solve this for the optimal output level of the intermediate goods producer if we bring xt to the left hand side and all the rest to the right hand side. And that solves for an xt as a function of at times L multiplied by a constant term that is equal to alpha to the power of 2 divided by 1 minus alpha. The individual steps for this calculation can be easily seen. So we bring first the -1 to the right hand side. So we have then +1 on the right hand side. Then we divide by alpha squared atl to the power of 1 minus alpha, which we have then on the left hand side 1 divided by this term. Then we want to get rid of alpha -1 in the exponent, so we raise the whole expression to the power of 1 over alpha -1. So we would get 1 divided by this expression to the power of 1 over alpha -1. And then we can change numerator and denominator and multiply the exponent by -1. These two operations exactly offset each other, and then we would get exactly this expression here, 2 alpha to the power of 2 divided by 1 minus alpha times atl. Now we can calculate some intermediate results. First, the profits of the intermediate goods producers. When we plug in xt that we calculated on the previous slide, so optimal xt, optimal output, into the profit function, so then we get here the price that's also plugged in from here, from this expression, multiplied by x, that's this expression here, and then we subtract x again from here. Now you see that something simplifies. So if you take the product of atl to the power of 1 minus alpha and atl to the power of alpha, this becomes atl. We have atl in this term and atl in this term, and we have an expression that involves alpha and an exponent in both terms. And if you do the calculations, you can simplify this to 1 minus alpha times alpha to the power of 1 plus alpha divided by 1 minus alpha times atl. So that's the expression then for the profit of an intermediate goods producer. Then we can also plug in the expression for xt from the previous slide again into the expression for output. So here into this xt. Then we get this xt to the power of alpha. So again we have atl to the power of 1 minus alpha here, atl to the power of alpha here, and we have the expression alpha from this here, but to the power of to the power of 2 divided by 1 minus alpha, but then again to the power of alpha because of this alpha here. So this is then alpha to the power of 2 alpha divided by 1 minus alpha. And then this is just this expression. And finally, we can compute GDP which is output minus the intermediate inputs, the value of the intermediate inputs, xt. So we again plug in for yt from here, for xt from the previous slide, and then just simplify, and this expression then becomes alpha to the power of 2 alpha divided by 1 minus alpha times 1 minus alpha squared ATL. The important point to notice now is that we have that L is constant and we have here a constant term. So we immediately see that the growth rate of output and the growth rate of GDP would be equal to the growth rate of A. So the growth rate of productivity determines again the growth rate of output and of GDP, and since the population size does not change in the model, also of per capita GDP. Now we have to determine how innovation behaves and how the change in A is brought about in the economy. And so here it's a model of purposeful research and development investment. So we have an innovator that attempts an innovation to create a more productive intermediate good. So you can imagine this, there is an intermediate goods producer that produces a certain intermediate good, and then an outside inventor says, okay, I try to produce a better product and I try to drive the previous incumbent out of the market. Now, if the innovation is successful, then the productivity of the intermediate increases. So let's say the previous incumbent had a productivity of AT minus 1 of its intermediate. Now, if innovation is successful, then AT will be gamma times AT minus 1, where gamma is larger than 1. So that means that a successful innovation leads to a more productive intermediate. The problem, however, is that research, of course, is uncertain. So there is only a probability of a successful innovation that you can influence. So if you are the outside innovator, then you can invest in research and development, and your investment level is denoted by RT. But this does not necessarily in a deterministic way lead to a new innovation, but it just raises the probability for an innovation. And what's also assumed in this model is that it's not the absolute level of expenditure that matters, but expenditure normalized by the level of technology that is already there. So if technology is more sophisticated already, then you need more resources to invest in order to have the same probability of a successful innovation. Now AT star is the productivity level, or A star, if the innovation was successful in the previous period. So that's then gamma times the previous period's productivity level. Now mu t is the probability of a successful innovation, and phi is a function that depends positively on this research expenditure normalized by the productivity level in the economy, or normalized by the state of technology. Now, to save on notation, Aghion and Howitt define this ratio of research expenditures normalized by the level of technology as n. And they assume, for later on, a Cobb-Douglas specification of this function, where phi of n, so the function that translates research expenditures normalized by productivity level into the probability of a successful innovation, as lambda times n to the power of sigma. Lambda can be interpreted as the productivity of research, and sigma is between 0 and 1 and introduces a concavity of this function. So we would have that the derivative of the function phi with respect to n is positive, the first derivative, but the second is negative. So you have a concave function where the probability of a successful innovation raises with the resources that an innovator spends on innovation, normalized by the current state of technologies. Now we can compute equilibrium research spending, or the optimal research spending of this innovator. The expected reward from innovation for this innovator is the probability that its innovation will be successful, so phi of n, multiplied by the profits that it can get with a successful innovation, which is pi t star. So we can plug in from what we had previously. So the function phi depends on the resources spent on research and development divided by AT star multiplied by pi t. So that's the expected reward. And the net benefit is if we subtract from this expected reward the expenditures, the resources that you invest in R&D, so minus RT. Now the innovator maximizes with respect to the choice of R&D spending, RT. So it takes the derivative of this expression here with respect to RT. Now if we take this derivative, we see immediately we get the outer derivative, phi prime of RT divided by AT star, and then the inner derivative is 1 over AT star. Then this is multiplied by pi t, so we have here the ratio pi t star divided by AT star. And here we have minus 1, that is from the derivative of this expression here with respect to RT, and that is equal to 0. So it's the first order condition. That's the condition that has to be fulfilled for a maximum net benefit of research spending for the innovator. And then we can plug in the expression that we had for profits, pi t, that's as we've derived it previously, 1 minus alpha, alpha to the power of 1 plus alpha divided by 1 minus alpha, times at. Now since this is pi t star, this is also at star, times L. So if we plug this in here, we see the at star and the at star in the denominator, they cancel each other off. And then we can just denote this parameter cluster here, 1 minus alpha times alpha to the power of 1 plus alpha divided by 1 minus alpha as pi. And then we get the first order condition here as the derivative of phi with respect to research spending and times pi L. And that has to be equal to 1 for the optimal level of research spending of the innovator. Now we use this Cobb-Douglas specification that Aghion and Howitt suggested for phi n, that we know from one of the previous slides here, and take the derivative of this expression with respect to n. So the sigma from the exponent comes down and the exponent is reduced by minus 1, and that's exactly what we have here. So for the derivative phi prime of n. And then we plug this into the first order condition from the previous slide, so here. And then we can solve the result for n, so for optimal research spending normalized by the level of technologies. And that would then be equal to sigma divided sigma times lambda pi L to the power of 1 over 1 minus sigma. And then we can finally use this n, which is the optimal n that an innovator chooses, by plugging it into the innovation probability into the function phi n again, and computing the research productivity then, which turns out to be lambda to the power of 1 over 1 minus sigma from here. And then sigma pi L, which is raised again to the power of sigma. So the exponent here is sigma divided by 1 minus sigma. And that's now the equilibrium innovation probability that you have at equilibrium at time t. And since the right hand side here is constant, it holds for all time periods t. Now, overall, we are interested in growth of per capita GDP, so we can divide GDP by L. And as I've shown previously, this just amounts to cancelling L out here. So we have that GDP divided by L is a cluster of parameters determined by alpha times AT. So the growth rate of per capita GDP would be equal to the growth rate of A at time t, which is at minus 1 divided by at. Overall, we are interested in per capita GDP and the evolution of per capita GDP or growth of per capita GDP. So we divide GDP by L, and for GDP we already know the expression from one of the previous slides here. So we just need to divide this expression here by L to get per capita GDP. That's exactly this expression. Now here we see this is a cluster of parameters determined by alpha, so that's constant. So per capita GDP grows at the same rate as the rate of technological progress, so as productivity grows. So GT would be the productivity growth rate. That's AT minus AT minus 1 divided by AT minus 1, so the definition of the growth rate of A. Now, however, growth is random because it only occurs sometimes. So there is a probability of a successful innovation, but this probability is not equal to 1. It's equal to a number between 0 and 1. So there will be periods without innovation and there will be periods with innovation. That's a consequence of the one sector specification. Later, for the multi-sector specification, we will see that due to the law of large numbers, actually there is a fraction of firms that would have a successful innovation at each point in time, and that smooths out innovation over time. But here we have that growth occurs with probability mu. That's a successful innovation. So in this case, we have that the growth rate of the economy is equal to AT, which is then gamma times AT minus 1, minus AT minus 1 divided by AT minus 1, and that's nothing else than gamma minus 1. So that would be the growth rate of the economy if the innovation is successful in period T. However, with the probability 1 minus mu, we would have that AT minus 1. So AT is equal to AT minus 1. There is no innovation. And then, of course, the numerator here is equal to 0. So the growth rate of the economy would be equal to 0. And then we can compute expected growth over time, G, which is the expected growth rate, E of GT, and that would be the probability of a successful innovation, mu, times the growth rate if the innovation is successful, which is gamma minus 1. So we have the expected growth rate of the economy, mu, times gamma minus 1. And then we can plug in the expressions that we had for mu, which was from one of the previous slides here. So that's this expression that we plug into the expected growth rate. And then we get the expected growth rate in the economy just as a function of parameters. So it's an explicit expression. It's solved explicitly. We have the long run economic growth rate in the economy. Now we see the long run growth rate of the economy would increase if researchers are more productive, which can be interpreted as higher education. So the better educated scientists are, the higher would be their productivity, and that would raise economic growth, ceteris paribus. The larger the innovation step size is, would also lead to a higher growth rate. If the population size is larger, we would have faster growth rate, so that's comparable to the Roma model. So there is a strong scale effect in this version of the model. I will talk in another lecture later on about the version of the model where we can get rid of the scale effect. Then pi is related to the profits that you can get with a successful innovation. So it's the incentive to carry out R&D. If this is higher, then also equilibrium growth would be higher. And sigma was the parameter of the probability of innovation, basically, as it depends on the resources invested in innovation, and of course if it's higher, then also the growth rate would be higher. So to summarize, we now have a second model that can explain long-run economic growth, now with vertical innovation as compared to the Roma model, which had horizontal innovation. So in the Roma model we had that each innovation is the introduction of a new intermediate good. And in this model, we have that each innovation is the introduction of a superior intermediate good, basically. The implications for the long-run growth rate are, however, very similar. So we have similar effects here. So the two models predict very similar policies that would lead to a faster economic growth rate. The main differences from a technical perspective are that here innovation is stochastic in a certain sense. So we could have also cycles of innovation and all that kind of things. And that we have this Schumpeterian effect that old incumbents are driven out of business, so we can model this effect of creative destruction. Now, what is not so nice in this version of the model is the one sector specification that leads to an on-off economic growth type of evolution over time. So we either have economic growth in a period or not, but this is not what we observe in reality, where it's rather smooth. And in the next video, I will introduce a multi-sector version of the model, which has, as we will see, exactly the same implications. Almost everything stays the same, but we have a continuum of intermediate goods producers, and that smooths out the growth rate over time. So we would have always a share of firms that innovates, and this share of firms could be very different firms in one period from the next period, but it's a constant share, an expected fraction of innovators in the economy, and that would lead to a smooth growth rate over time. Thank you very much for watching the video, and I hope you found it interesting and useful. For more videos on economic content, please visit my channel that you find here to the left. And to the right, you see the next video in the series at the top, and at the bottom, you see the whole lecture in the form of a playlist.